Hi Professor, I'm Shivani and today we are here to present our project on road collision severity in Southern Australia. At some point in our lives, we've either witnessed a road accident or been in one, or at least know someone who's been involved in one. That's exactly why this study is important. With road networks growing and traffic increasing, accidents are inevitable. But what if we could predict the factors leading to severe crashes? What if data could help us make our roads safer? In our project, we analyzed road collision data from 2019 to 2023, uncovering key trends in accident severity, casualty demographics, and vehicle improvement. By leveraging real world data, we aim to extract actionable insights to improve road safety. If given a chance to reduce road accidents, what factors would you focus on? Speed limits, road conditions, or driver behavior? These are exactly the type of questions our study explores. Our analysis covers identifying trends and patterns in road collisions, examining factors like driver demographics, injury severity, and external conditions. Also, understanding impact of weather, vehicle type, and time of day on accidents. Let's meet our team. So we have Ashwin Sudhakar, who is our project manager. Then we have Rinsia Ibrahim, our data analyst. Myself, Shivani Sailod, data engineer. Verghese George, data scientist. Now coming to our team communication channels, to stay coordinated, we use multiple communication platforms. WhatsApp for quick updates, reminders and real-time discussions, Microsoft Teams for structured meetings, file sharing and formal discussions, Google Meet for virtual meetings, remote collaborations and presentations, and in-person meetings for brainstorming sessions in the college library for finalizing key aspects. This multi-channel approach ensures smooth collaboration and timely project completion. Our study is driven by three key research questions. What factors influence the severity of traffic collisions? So this helps us in categorizing human, vehicle and environmental causes. Then second we have how does seatbelt and helmet usage impact injury severity? So this helped us understanding the role of protective measures in reducing injury impact. Then we have third as how do weather conditions and time of day affect accident severity, analyzing how external factors contribute to car crash risks. These questions guided our data analysis and helped us uncover meaningful insights for improving road safety. Next part would be explained by Ashwin.
My name is Ashwin Sudhakar, and we'll be talking about the design phase of the project. I'll be doing the cleaning of data. So that's our data source. And we'll be basically removing the null values, improper data types, relevant data, and ensuring at last will be ensuring all the data sets matches with the report ID, which is the unique column and row that we have in our like throughout all the three data sets that we have. So just to have an idea, that's how our data set looks at the moment. Like we have, as I mentioned, we have three. I'll be talking about one because all the other two basically follows the same rule for cleaning. And so that's the report ID that we have, which as mentioned is a unique one. And as you can see, there are blanks. There are blanks all over here. So to remove, we initially thought of removing the entire column, but this is pretty important to know about the status of the safety, like seatbelt and helmet. So we had to fill data where the empty columns are here. Like all the empty column has to be filled with not applicable, so that we still can use those things. So yep, and we also had X values over here. So just to see that's in the code, this basically prints out as how it looks like in the Jupyter notebook when we when we show the data set before cleaning. So that's pretty much about it. And then we started cleaning. So here we load the data and then we display a few rows just for information, and then we started handling missing values. So to sum up, these are the missing values that we have at the moment, and then we drop the columns with X values as shown in the other window, and we had to check for duplicates and remove them if any. So we did remove a lot of duplicates that we had, and that's done. And we had to convert another thing is that we had to convert each column and rows data into numeric for easy calculation and easy interpretation. And after cleaning, that's the value that it's clean. There is nothing null, no repetition, no duplicates. So that is that. And so it the PPT over here talks about the different stages that we followed for each data set. So data cleaning continuation for the crash, and now we are talking about the unit. So basically, it follows all three data sets follows the same rule, and final combine. So this portion is pretty important to understand because what we did here was we combined all three data sets based on, or we cut short, or let's say we cut short all the data set after cleaning with the unique ID, so that every data set after cleaning matches the exact number of rows that we have. So over here you can see the final data sets after cleaning, and this is based on report ID. So I will show you the code for that in a moment. And here, as you can see, what we did was we initially displayed the initial dataset shapes. So that's how it looks: 63,000, 99,000, and all were the number of rows. And we matched with the matching report ID, which make it down to 16,013 rows. So that's what we did. We keep only the matching report IDs in each dataset, and then we ensured all datasets have the exact name, number of rows, and then we displayed the data sets. So as you can see over here, it's 16,013 for all the data sets, regardless of the columns that we have. Columns, we can't remove the columns like rows, since columns speak a lot different in all three data sets. So we kept the important columns, we kept the columns there, but made sure the rows are sorted throughout the all three data sets. And then we finally clean the data sets and then print, and that's where we clean the thing. So here, after cleaning, you can see that the data set has become absolute important. I mean, absolute easy to understand. Like there are no null values, there are no blanks, there are no X values, and as I mentioned before, the helmet and seatbelt, which was pretty important, has been filled with unknown and not applicable wherever needed. And then everything is sorted out here. So that's what we did in the cleaning and final cleaning portion. And that's pretty much it. Thank you. Next part is feature selection, which comes under design phase and which will be explained by Shwani.
Now that our data is cleaned, we move to feature selection, choosing the most relevant variables for predicting collision severity. In our process involved, extracting key attributes from crash unit and casualty datasets, using correlation analysis to determine high impact factors, removing redundant or low impact variables to improve efficiency. By selecting only the most relevant features, we ensured our predictive model would be both accurate and optimized. Our Python code loads, filters, and saves clean datasets, retaining only key variables. We then generate summary statistics using describe function, providing insights into distributions, averages, and the extremes of features like age and vehicle year. This helps us detect outliers, imbalances, and missing values, ensuring data readiness for modeling. To optimize our dataset for predictive modeling, we carefully selected the key features while eliminating the redundant ones. From casualty dataset, we retained attributes like casualty type, age, sex, injury extent, seat belt, and helmet usage, as these directly influence the accident severity. In the crash dataset, we focused on weather conditions, time of day, crash type, and DUI involvement. These factors are significantly impact accident likelihood and severity. For the units dataset, we kept vehicle type, vehicle year, driver's age and sex, unit movement, and number of occupants, as these variables affect crash dynamics. Now, next part would be presented by Rinsia.
Hi, my name is Rinsi Ibrahim. Now let's dive into the exploratory data analysis and visualization segment of our MRP. Using the data prep library, each feature of the casualty dataset is visualized here to analyze its distribution, patterns, and potential correlations for better insights. Here, this bar chart shows the severity of casualties from road collisions. Most people were treated at the hospital, followed by those who received private care or were admitted. Fatal cases were the least common. This suggests that while many road accident victims need medical attention, most injuries are not life-threatening. Here, each feature of the crash dataset is visualized to analyze its distribution and patterns. Here, this bar chart represents the distribution of road crashes based on weather conditions. The majority of crashes occurred when it was not raining, while a much smaller number happened during rainy conditions. This suggests that road accidents are more frequent in dry weather, possibly because there are more vehicles on the road, or drivers may take fewer precautions compared to rainy conditions. So similar to the other two datasets, each feature of the units dataset is visualized to analyze its distribution and patterns here. This histogram shows the distribution of vehicle manufacturing years in crashes dataset. The crashes involving older vehicles are low, while those with the newer vehicles are significantly higher. The peak around 2010 to 2020 suggests most crashes involve newer cars, likely due to their higher presence on the roads. The slight decline after 2020 may be due to fewer such vehicles being involved in accidents. Here, this graph displays the top 10 accidents by vehicle type, with sedans leading, followed by station wagons. Utility vehicles and motorcycles also show high accident counts, but far fewer than sedans. Commercial and heavy vehicles have fewer accidents, likely due to professional driving standards. The data highlights private passenger vehicles as the major contributors, while motorcycles remain vulnerable. The next portion will be presented by my teammate Varghese. Thank you.
Hello, my name is Wagis George, and I'm here to present the development phase. And going to the slide, first we started importing the libraries such as pandas, matplotlib, seaborn scaling, and stat model for the data manipulation, visualization, and predictive modeling. Then we loaded the three datasets, and we displayed some of the rows from the dataset. And then extracting the year and month, like we have a report ID column in it. We extracted the year and month to enable time-based trend analysis. We use string extraction technique to get the 3-month and month values. Finally, we convert the numerical format, and the output show the extracted years and month values, confirming the successful processing. And in the predictive visualization for the data sets, we have 3 charts for that. Into that, first is monthly trends of crash over time. Like we aim at analysis crash frequently trend over time. We aim to ensure that with the crash data set, and we plotted a time series graph, which is for peak and accident months. The graph shows a sharp rise and falls in crash, indicating the seasonal or external factors affecting the accident frequencies, like graph you can see here. And the next one is time series analysis. We have performed the seasonal decomposition of time series, which has original trend component, seasonality, residual. This is the code for that, and the output was like this. The decomposition graph really shows the trend increase peaking in late 2019 and early 2020. A seasonal pattern with fluctuation happening at the regular intervals. Residual the variations, meaning the external variables also influence accidents. The confirms time of year significance impact of crash severity and frequency. And moving to the next slide, like we merge the crash unit and casualty data sets based on the report ID for the analysis. After merging, categories were encoded into the numerical format. We conduct a correlation analysis to identify the most relevant features affecting the crash severity. This was a crucial step in the accurate predictive model. Like this is the visualization, like the heat map visualization for the correlation metrics, and for the strong relation between factors like weather conditions, seatbelt usage, and crash severity. A clear pattern of which variable influence accidents outcome the most. The analysis helped to determine the most important predictor of our model. And going to the next, it's model accuracy. We use the random forest classifier, which dataset was split into training and testing, which was 80 and 20 offsets. The model achieved 97.6% accuracy, which is very high. The classifier reports the predict and recall value of 0.95%. Sorry, 0.95. The model was accurately predict the crash severity based on the input features. And next is the challenges we faced in the past, current, and the next phase. For the current and past, these are the some of the important, like the understanding factors relationship, duplicate records in crash data, inconsistent categorical data, unaligned records, and we solve that using cross tabulation. We remove the report ID, age plus injury, and we standardize the level of the weather condition, other category joins of the consistency, and yeah. Then for the next phase challenges, we have some like qualifying factors, like we apply the cheat-coded test to validate the relationship between the crash factors, and use ANOVA and the trend analysis to track changes from 2019 to 20, and utilize the bar chart, heat map, and severity graph for the clear data visualization. And that's for me, and I invite the Rincia for the next slides. Thank you.
Hi, it's me Rinsi again. Now let's look into the recommendations. For the current phase, to ensure data accuracy, duplicates should be removed, categorical variables standardized, and missing values in injury extent, seatbelt usage, and vehicle type addressed. For analysis, evaluate the impact of seatbelt or helmet usage on injury severity, assess how weather and time of day affect collision severity, and compare vehicle types to see if larger vehicles lead to more severe crashes. The next phase involves analyzing trends from 2019 to 2023, focusing on seasonal patterns, severity changes, and peak crash times. We will use heat maps, bar charts, comparison charts, and severity distribution graphs to examine factors like seatbelt usage and weather conditions. Now let's look into the project cost. Looking at the graph, the design phase had the highest cost, followed closely by the requirement phase. The development phase, which is still ongoing, has reached $772 so far. While the early phases required higher upfront investment, we can expect development cost to rise as work continues. And beyond development, we will still have testing, release, and deployment ahead, which will add to the total project cost. So here are the links for our presentation. Thank you.